finds you well, you and your loved ones. Once again, the Lord is risen. Alleluia, alleluia. Truly he is risen. Alleluia, alleluia. If you ask me why are you happy in such a dark times, well, this is especially the good time. This is especially a time to be happy. All right, because Jesus, by rising from the dead, has conquered death. All right, so this is a joyful moment. All right, okay. So yesterday you had four problems. Any questions? Yes, Aditya?
Yeah, I think it was number 43.
Okay, so 43. Okay, any other one? Leo?
Can you do question 44?
I cannot hear. Leo, cannot hear. Leo, can you chat or something like that? Okay, Max?
Number 41, and I also have something in specific to ask about 42.
Yeah, well, we'll see. Okay, Leo, say 44. So you want me to do all of them, basically? Stephen?
I was gonna ask 44 too.
44. Okay, so everything except 42. Okay, all right. So let's do 41 here. Just let me see here. There's someone who wants to chat. Okay, that's my screen is not big enough for. Yeah, Max, you can lower your head. Okay, so let me sort of share the screen here. Okay, so let's start with 41. So 41, a 5 kilogram rock is dropped from a height of 92 meters. So this is your initial height right here, 92 meters. What is kinetic energy and gravitational potential energy when the rock is 40 meters from the ground? So that's the final is 40 meters. All right, good. All right, and yeah, and then we know the mass too. So the mass is 5 kilograms. Whoops. 5 kilograms. Okay, so of course here you, when it says it's drop, it means that the speed is 0, all right? So if the speed is 0, so that means that kinetic energy, the initial kinetic energy is 0. Let me just, okay, let me put this on this side here. Raymond Lee, there we go. So of course you applied like conservation of mechanical energy. So mechanical energy before is equal to mechanical energy all throughout, actually all throughout this, the drop, the mechanical energy stays the same, all right? So this is kinetic energy plus gravitational potential energy is equal to final kinetic energy plus final gravitational potential energy. As we said earlier here, so this is 0 here. And then you just put like your formula. So mghi is equal to, you're looking for what? You're looking for kf and ugf. Okay. Yeah. So kf plus mghf, right? So of course the final kinetic energy, the final gravitational potential energy is just this using 40 meters, so 5 kilogram times 10 meter per second square times 40 meter. So that'll give you like, I think 200 joule, if I'm not mistaken. 20, yeah, no, 2000, yeah, 2000 joule. All right, and then we're looking also for kf. So you isolate for kf. So it'll be so if you bring this on this side here, right? So you'll have you'll have like this minus this, right? So we already know like the final, the initial. Well, you just put this in, all right? So you just use like HI equal to 92, and then you figure out what the kinetic energy is. The kinetic energy at this point is. Okay. All right. So number 43. Let me do 44 first. Okay, I'll come back to 43 in a second. So 44. So what do you have here? Is this? So you have this this ride, and it swings all around. You're given the diameter of the circle. And what you want to find here is you want to find what should the speed at the bottom be so that it makes it just to the top, right? So it makes just the top. So what does it mean to make it just to the top? Well, you want the speed here to be 0 meter per second, right? That's how it goes, all right? You're given the diameter. So the diameter here is 30 meter, right? Swings in a circle. All right, so let's look at the forces here. I forgot to give my system here. The system will be the mass and the Earth. Okay, so let's look at this here. If you do the FBD of that, what you have here, you're going to have FG, and you've got to also have like this force provided by the rails, by the beams, whatever it is, right? Okay. Now, can anyone sort of tell me why we don't care about the force exerted by the beam? Why we don't care about the force provided by the beam here? Anyone? So why don't we care about that? Oh, no one answers? Yeah, Jason.
It's perpendicular to where it's moving.
Yeah, this is a constraining force, right? So it's always 90 degrees perpendicular to the direction. That's correct. So it's 0. It's constraining force. The beam here is there. The force provided by the beam is there to make sure that this ride goes on a specific path, specific trajectory, right? And this is what we define a constraining force. Constraining force is a force that forces an object to go along a particular path, and work done by constraining force is always 0. Okay, so what you do here is, of course, your system will be the Earth, right, and the wagon, whatever it is, like I don't know, the ride. Okay. Madav is back. I don't know where you went. All right. So you just apply like conservation of energy. So you have this here. So this is Ki plus this is equal to Kf plus that. At the top, of course, it's 0 because, sorry, not this. Sorry. Yeah. I don't know if I can undo something. All right. No, not black. F. So at the top, of course, this is 0 because this is 0 here. And then if you consider this as your reference level here, the initial gravitational potential energy will also be 0, all right, because HI is equal to 0 meter. So you're left with this. You're left with the initial kinetic energy is equal to this. So it'll be like this is equal mghf. So of course the mass here cancels. And what is HF equal to? HF is equal, of course, to 30 meters. That's it. So you just put this and solve for VI, and you're gonna see like what's the minimal speed that this object must have at the bottom, so it can make it, at the very least, can make it to the top. All right. Very good. Okay. All right. So give me a shout if you're not certain here. Okay, so number 43. All right, so here's the basketball. Okay, so that's the basketball. This is the ground right here. And it falls from a height. And I'm going to call this height here H1. You'll see why. All right. So it falls. And as it falls, all right, so that falls, it will have a certain speed just before hitting the ground. But what you notice here is that during this drop, of course, you neglect air friction. The mechanical energy is conserved, right? So during the mechanical energy is conserved. So let's call this mechanical energy at this position 1, and let's call the mechanical energy just before it hits the ground, M2. So what do we have here? Well, we have K1 plus gravitational potential energy. This is virtually 0 here because it drops like from 0. So all the mechanical energy is in the form of gravitational potential energy at the top. Now at the bottom, what do we have? At the bottom, well, of course, gravitational potential energy is 0 if you consider this as, if you consider the ground as the reference, and everything is in terms of kinetic energy. All right. So this is just before it touched the ground here. Okay. So what do we have here is, as it falls, we have M1 is equal to M2, right? Or okay, so we have this. Now, next stage. So next stage is it collides with the ground and loses 15% of its kinetic energy. So here, this is as it goes up, all right? Now, it says that it loses 15% of its kinetic energy. So if it loses 15% of its kinetic energy, so the kinetic energy on its way up, if it's 15% less than it was before, right? So it was K2, right? Just before it, right? So 15% less. How will the kinetic energy on its way up, right? Like here when it leaves the ground, how will the kinetic energy here compare to the kinetic energy right here? Anyone? So if it loses like 15%, so I want to give me an equation here. Madav? Well, David, yeah, let's do David. David. That's correct. So very good. So 0 point, all right? So what you know here is you know that the kinetic energy, and it's just as it leaves the ground, it will be 85% of what it was before, K2. Now it goes up. So it goes up and it's not going to go as high. All right. All right. So we're going to call this like H4. And of course here, like the mechanical energy. So on its way up, the mechanical energy is all in the form of kinetic energy. Right here, the speed is 0. So the mechanical energy at the top is equal to all in the form of gravitational potential energy, right? And of course, on its way up, mechanical energy is conserved. So you have M3 is equal to M4. And so that means here that K3 is equal to UG4. K3 is equal to what? K3 is equal to 0.85 times K2. So I'm going to put this right here. So 0.85 times K2 is equal to this. All right. Now, K2, so if I go back to this one here. So mechanical energy at first is all in the form of gravitational potential energy right here. And just before it hits the ground here, it's all in the form of K2. And these are equal to each other. So what do we have here? We have this is equal, the kinetic energy just before it hits the ground is equal, it looks like an insect. There you go. It looks like, so the kinetic energy but just before it hits the ground is equal to the initial gravitational potential energy. So if I put this right in here, I have 0.85 times this equal to this. There you go. So if I put the formula here, so mgh1 is equal to mgh4. So you can see here that mg cancels, and then where you're left with the fact that the final height will be 85% of the original height. All right. Okay. Yeah. So it'll be, so what we did here, we use conservation of energy on its way down, and conservation of mechanical energy on its way up. All right. Yes, Forrest. Yeah, Forrest. Forrest. Yes. Cannot talk. Forrest. Okay, Madav. I don't know why. You can chat.
Can we solve this?
Okay, yeah.
Can we solve this problem using ratios?
Well, it's because you have to go through the whole thing. I mean, you cannot, like, it works here with ratios because the gravitational potential energy is proportional to the height only, but it's only a special case here, all right? It's only a special case. Yes, Forrest. Yeah, I expect to show all these diagrams for these questions, yes. So yeah, it's only a special fluke here, like it's just because of the form of the potential energy that you can do ratios. But basically, you have to show that why this is true, and you have to show this with conservation of energy. All right. Okay, are you good? Any other questions? Okay, so. All right. Okay. So I'll just leave the group chat here. Okay, so let's go back to what we learned yesterday. Is Catherine here? I don't remember. Did I see Catherine? Are you here, Catherine? Where's Catherine?
Yeah.
Oh, you're here? Okay, good. All right. Okay, so let's go back to yesterday here. So yesterday we look at the case where you have non-conservative forces being present. Not only conservative forces, but also non-conservative forces. So an example of this would be like a roller coaster along with friction. All right. So once again, like the net work on an object of mass m can be grouped. So you have like various forces acting on the object. You can group all those conservative forces together, all the non-conservative forces together, and you can sort of group the work done by all conservative forces together plus the work done by all non-conservative forces together. Now, the key advantage of work done by conservative forces is that it depends only on where you start and where you end up, right? It doesn't matter how you went from the initial configuration system to the final configuration system. So you can replace this by a function that we call the potential energy function, all right? So we did this right here. We put this on this side. And then when we notice here, we notice that when there's non-conservative forces present, the mechanical energy of a system will not stay the same, will not be constant, will not be conserved. All right. By the way, here, does anyone know, like perhaps now by looking at this, does anyone know why physicists define the work done by conservative force as being equal to the negative of the potential difference of potential energy, instead of defining it as plus delta U? Does anyone know like why? Physicists could have defined the work done by conservative forces as being equal to the change in potential energy. Why did they put like the negative sign in front? Anyone? Okay, I have Madav, but I'll wait so some more people might know. No? Madav, yes?
Is it because in the end, when the potential energy is changing in one direction, the kinetic energy is changing in the opposite direction?
Okay. Yeah, kind of. Kind of. Yeah, Eric.
Is it because you have to do work to
No.
move something from?
No, just okay. I'll give you a hint here. Just look at my derivation here, and ask yourself if it was plus here, what would happen? Anyone? If this were plus instead. Just continue my derivation here, but if it was plus. No one?
The change in energy would be 0.
Okay, no. Okay, so if they had defined this as positive, yes, Stephen.
And like the final potential energy would be bigger, which means it's
Okay,
like
okay,
higher.
all right, that's okay. Max? Do you have something?
Oh,
No?
sorry, I didn't mean to do that.
Okay. All right. Okay. Physicists could have defined the word of conservative force as being equal to the change in potential energy. Nothing will have changed except that if it were like if the negative sign did not exist here, when I put this on the other side, it would have been kinetic energy minus potential energy. So they would have had to define mechanical energy as kinetic energy minus potential energy. It's much more like intuitive to add energies together than to subtract. So that's the reason why they chose like a negative sign here. Okay. So they chose a negative sign here so that the mechanical energy is defined as kinetic energy plus potential energy. If they had defined work done by conservative force as delta U, they would have had to define mechanical energy as kinetic energy minus potential energy. All right, and it's just so more natural to add energies than to subtract. So that's the reason why. Okay, all right. So you're good with this? Okay, so let's look at let's continue here. So remember, like work done by friction, by bad friction, by distributive friction is a non-conservative force. All right. So let's have like a general case here. So no. So let's have something like that. All right. So this is a slopes right here. Let's see here. This is an object that slides down. And then we're going to have friction acting on it. All right. Ah. Ugh. All right. So. Okay. So this is an object here sliding down. There's friction acting. Wow, should be like should be straighter on the bottom. Make this straighter here. I thought I was doing I was drawing crooked lines only on a blackboard, but I guess I don't. Okay, so the key point here, and we're going to sort of say here that this distance here is the distance over which friction acts. So remember, the distance over friction acts was S, remember, or delta S. You know, you can put like S, doesn't really matter here. Okay. So the work done by friction, is the friction times the distance over which friction acts. And you can see here that the friction is always 180 degrees opposite to the direction of motion. So what we're going to have here, we're going to have a cos of 180. And of course, cos of 180 is -1. So the whole thing here is that we get this. All right. So where S is the distance over which friction acts. Friction acts. All right. All right, so work done by bad friction, distributive friction is always negative. Okay, it always helps to slow down an object, never to speed it up. All right. Now recall that the change in mechanical energy is equal to the work done by non-conservative forces, right? So that's the general formula here. And when there's only conservative forces, well, this is equal to 0. So you get conservation of, right? So when there's only conservative force, whoops, this is equal to 0, and the mechanical energy is conserved, right? In most of the cases, most of the time, the non-conservative force you're going to be dealing with is a friction only. Okay, so if friction is the only non-conservative force, let me see here. Non-conservative force present. Whoops. So friction is the only non-conservative force present. Then what we have is this. All right. And most of the problem you're going to do, it's mostly this. When the only non-conservative force we're going to put is friction. But sometimes you have to be careful, though. There could be an applied force, right? It could be a tension. But most of the time, it's going to be friction. Now, since the work done by friction is negative, what it means here, it means this. Whoops. Or So what happens here is that in presence of friction, mechanical energy is lost. All right, it is lost. All right, so you can find here there's mechanical energy. Change in mechanical energy is smaller than 0, so this mechanical energy is being lost. However, you've learned, and we're going to talk about this in greater detail here, but you've learned in elementary school something about energy. What did you learn about energy in elementary school? Don't tell me you didn't learn anything. Yeah, Leo. Leo?
Energy can't be destroyed, only
That's
transformed.
correct. All right, so that cannot be destroyed nor created. Very good. All right, so I'm going to ask you here. When there's friction here, there's a loss of mechanical energy. So where's this lost energy gone? Because you've learned that energy is neither created nor lost. So here we have mechanical energy being lost. So where does it go? Okay, Jason?
Turn into heat.
I cannot hear.
Turn into heat.
That's correct. Thermal energy, right? Yes, that's exactly it. So when I do this here, I generate thermal energy. All right, so friction here, because of friction, I generate like thermal energy. And this is exactly it. Yes. So the loss of mechanical energy here, whatever has been lost mechanical energy, is being converted into thermal energy. That's very good. All right. So what we'll do here, we'll do a sample problem. It's a pretty, it's going to be short today. So what we're going to do is we're going to do a sample problems involving this. So it's going to be the same roller coaster as before. But now we're going to put friction here. Okay, we're going to put friction. So, example. So, example. All right. For the same roller coaster as before. Same roller coaster as before. So find the speed of the coaster at the end of the ride. If a constant frictional force of, so let's see here, let's put 20 Newton. Frictional force of 20 Newton acts on it. And the ride covers a total distance of, let's say, 3 kilometers. I hope it's going to work. So once again, these are things that I'm putting out of my head here. Let's hope it's as easy to manipulate as before. So same roller coaster, same condition. It starts from 50 meter. It ends up at 5 meter from the ground. But the only thing that here that we have, in addition to this, is we have frictional force. Okay, that comes from the rails. That could also come from the air. All right, so let's do this here. So let's do the system. So it'll be the coaster, right? Plus the rails here, right? Plus the earth. Okay, I want the earth because I don't have to put the rails, but anyway, I want to put the earth because I want to make use of gravitational potential energy. Okay. I mean, you don't have to put the rails here if you don't want not put the rails. That's fine, but at least like put the earth. Okay. So I'll put this in brackets here. So this is. Okay. All right. So what we're going to do here is this. We're going to use conservation of mechanical energy, but since friction is is a non-conservative force, we know that mechanical energy will not be conserved. So what we're going to have here, we're going to have this. We're going to have change in mechanical energy is equal to the work done by non-conservative force. And in this one here, we have only friction. All right. Now let's put like some givens that we know. Oh, there's something else. I'll have to add. Mass of coaster is, with people in, is 1,500 kilogram. Do you remember before I did not need the mass because it canceled on both sides, but now here I will need the mass. So you'll see this in a second. Okay, so let's see what we have here, the givens. Well, we have we have the initial, let's put this here. We have the initial height, which is 50 meter. We have the initial speed, which is 0 meter per second, starts from this. We have also the final height, which is 5 meter. We're looking, of course, for the final speed. What else do we have now? What else do we have?
You have S.
Madav? No, Aditya. There we go. Aditya?
We have like the mass and
Yeah, the mass. Okay, so mass. Okay, what else do we have, Aditya?
also the distance it covers, which is 3 kilometers.
That's correct. So here, like the friction is the whole right? So the friction will act along 3 kilometers. So of course you have to change this into meter. And what else we have? Last one. Yeah, Max.
The force of friction is 20 newtons.
Yeah, 20 newtons. All right. So this is what we have. So let's do this happily. All right, so I'm going to put here, so I'm going to continue here. So it's going to be like this minus this equal this, right? Now here you're going to have like Kf plus the initial gravitational potential energy minus this equal to that. right? You can put this also in terms of delta K plus delta U, right? It's the same, right? You do whatever you feel comfortable with. We know it starts from RAS, so we know that this is 0 here. And then nothing else is 0. So let's put like the formulas here. So mv f squared over 2 plus mg final height minus mgh height is equal to this. All right. Now notice here that the mass cannot be canceled because you don't have mass here, right? So you cannot cancel the mass. So what it means here, it means that when there's friction involved, provided that friction is not proportional to mass, because it could, but if friction in general is not proportional to mass, then like the mass of a coaster will affect the speed, right? So a very light coaster will probably won't have as much friction acting on it. Well, no, it's not exactly true. Anyway, so let's continue here. All right, so I can sort of do some manipulation here. So let's factor out like m, if you like, out of all this. So this one here will be like plus g. I'm going to factor out like the g.
Is it VF squared?
It's VF squared. Thank you. All right, equal to that. Okay. It's just to facilitate the math later, but anyway, it doesn't really matter. Okay, so let's find the change in mechanical energy. The change in mechanical energy. Whoops, that's not what I want. But anyway, the change in mechanical energy is equal to the work done by friction. So let's find out like how much friction, how much work is done by friction. So it's going to be this minus 20 Newton times 3,000 meter. And if you do this here, you have 1, 2, 3, 4. So you have this. All right. So friction is doing minus 60,000 joule of work on the coaster. And this is how much mechanical energy will be lost by the time this coaster gets to the end of the ride. So what will happen here is that 60,000 joule of thermal energy will be created. So the coaster, along with you, right, you'll be hotter at the end of the ride. Not only because it was exciting and you sweat, but also because of physical consideration. Yes, Max?
But didn't you say like so when we were doing the unit with like acceleration and velocity and stuff that we have to like manipulate the formula before we can plug everything in?
Yeah, I know. I just wanted to show like, you know, how much it is, right? So
Okay.
before, that's all. All right. Okay. So let's continue here. So what I'm gonna do, so let's put this here. So let's do BB way here. All right. So BB way. Okay, so this one, yeah, we'll keep it like this. All right, so I'm gonna sort of send like the mass on the other side. Okay, I'll do baby way here. All right, so this. So I'll send this on this side. Okay. So let me sort of put some values here without isolating for VF like totally. So it's like 10 meter per second square. I hope it works. I think it works. The final height was 5 meter. The initial height was 50 meter. It's equal to this over 1,500 kilogram. So this one will give me a -4. So it'll give me -450 joules. Is that correct? Yeah. Ah, no, it's not joule. Ugh. Not joule. Joule. It's meter per second, meter square per second square, right? Right? Because you have a meter here times this. If I want to turn this into change in gravitational potential energy, I have to multiply by the mass. Okay, so let's do this here. So what do we have here? It's gonna be 600 divided by 15. What's 600 divided by 15, guys?
40.
40? Is it 40? Yeah. Wow.
Yeah, 40.
40. And joule per kilogram is nothing else but, well, let's put this here. So joule is kilogram per meter second per second square, and of course divided by kilogram. And as it should, of course, kilogram cancels, and you're left with meter per second square. All right. So you can only add apples with apples. Okay, not bad. So I didn't put like, I was concerned here if I put like too much friction, it would never get there to the right at the end of the ride, but it does. Okay, so now let's put this on the other side. So VF over square. So you put this one on the other side by changing the sign, and then you're gonna get 450 minus 40. So now if I do this like very quickly here, so I bring the 2 on the other side, right, times 410 meters square per second square. Unfortunately, it's not going to be as neat as before. If someone can, well, I can do it too. Let's see here. Yeah, Rolf, you got it? Yes, Rolf? Leo to everyone. It's a change. Yeah, thank you. Oh, that was a long, okay. Yeah, that's correct. So 28.6 meter per second. There we go. There you go. All right. So if you compare this to the speed that we had when there was no friction, right? Remember, when there was no friction, you remember here, the speed was greater. Of course, it was like 30. Well, it's a little bit lagging. There we go. So without friction, it was 30 meters per second. And of course, with friction, it has to be less, right? Questions? All right.
Sir.
Yeah.
In the diagram, how come you didn't account for friction moving forward? For example, like the traction.
Friction moving forward.
Moving the coaster forward.
Friction moving. I'm not so sure if I understand here. Friction is okay. Let me go there. Okay, come on. It's lagging. Lagging. Go back. There we go. So about this, like, I'm not so sure if I understand here.
So, because I remember you said there's friction always moving forward, for example, a car within the form of traction.
Yeah, but that's traction, right? That's not dissipative friction. That's good friction, right?
Oh, okay.
Like the friction that we're gonna mostly encounter is always like bad friction, dissipative friction.
So we never account for non-dissipative friction in these.
Well, if there were traction, then the work done by friction, by traction, would be positive instead of being like negative, right?
Okay, so we just ignore it for now then.
Yeah.
Okay.
Yeah. Yeah, it's like whenever you have problem with friction, it's always going to be dissipative friction. It's always going to be like bad friction. So bad friction. Wow, this is so slow. Okay, well, I'm done. So I'm going to assign like some problems. The problem I'm going to assign would be there'll be a handout. I don't know if I put it on the website. Let me sort of check here. No, it's not there. I'll put it, right? It says like do number 35 to 40 on handout. It's not there, but I will put it in after our meeting here. So you have to do these. And it doesn't involve friction. So it's only conservation of mechanical energy with conservative forces. But they're a bit more challenging than the one you did yesterday. Okay. All right. And then on Monday, you will have question with frictions. Okay. Good. Okay, so tomorrow it'll be a helping session. So Fridays, so I teach from Monday to Thursday, but Friday is going to be a helping session. And then for you guys, you're going to be happy here. For you guys, it's going to be like 9:45 to 10:45 on Fridays. Okay, so it will be like a bit earlier. So I will sort of send an invitation, but you respond only if you want help. Okay, I don't want like everyone like to respond. All right, so it is optional, and then it'll be one-to-one. So I'm gonna admit only one person at a time. Okay, so you have to wait your turn, and then I will admit the other person. Make sure that your video is working because I want to see you. Okay, and I want to talk to you, not only chat. So it's going to be between 9:45 and 10:45 on every Friday. On Monday, we'll continue. And Monday, as I said here, because of SL Economics, I put a super bright light now. It's going to be at 11:10, 11:15. Okay, so on Mondays, we're going to meet at 11:15 instead of 10:30. Okay. All right. And then Monday, Tuesday, Wednesday, and Thursdays, it'll be at 10:30. Okay, any questions? All right, so if I don't see you, I'll stay on like for another 5 minutes or so. So if you don't have any questions, I'll bid you bye, and have a great long weekend, and stay safe, stay home, and I'll see you on Monday. All right, so God bless. Bye.